So now we have this last type of noise, which is called as popcorn noise. And they say this noise is also called as burst noise or bistable noise or random telegraph signal or so many names. Burst, when something is unusual happening in a sudden flow of thing, you call it as a burst noise. So that is the name why this popcorn noise is also, when you make popcorns at house and you put the corn seeds and close it, and you don't know when they will burst and when the popcorn is got. So the bursting time is completely random, right? So same thing. That is the reason why these noise is called as popcorn noise. So predominantly we use only burst noise. All these other terms are very rarely used, and it is understood. Some people say it is same as flicker noise, but there is some correlation, but we cannot exactly equate the magnitude of flicker noise to popcorn noise. So it is mainly because of device contamination, or in a very technical term, you call it as doping in semiconductors. When you change the molecular structure of a semiconductor by doping, that you are indirectly increasing the conductivity. That is a very good plus point you get, but you also indirectly introduce noise into the semiconductor. So BJTs are often doped with gold, which is going to have very high level of burst noise. See, there are specific metals which you dope for a particular reason, for improving the conductivity, for improving the temperature performance. So we use different doping materials for semiconductors, and but the drawback of these doping will have effect on the noise. So once such serious effect is when you dope BJT with gold, it will have a highest level of burst noise, because the contamination by metal ion specifically will result in popcorn noise, because silicon is a semiconductor and gold is a metal. So this metal ion contamination is not going to be a good partnership. It is not going to create a good partnership for you. The device will work perfectly. It will have a very good collector current. It will have a very good VA characteristics. Everything will be perfect. But this metal ion bonding will indirectly generate burst noise, or we call it as a popcorn noise. So specifically, when you dope BJT with gold, this issue was found in dominating. This noise was found dominating. It was also found in diodes, normal diodes also. It was found tunnel diode also. It was found even in resistors, and predominantly when you see junction transistor, this noise is becoming very dominating because of the doping. Because all the semiconductors, we are doping them to make it extrinsic, right? N type or P type material, we dope it to make it extrinsic. So wherever you have this doping, depending on what compound you're going to use for doping, that will decide how much amount of popcorn noise is present or it can generate from the device. And again, this noise is completely, you cannot model it mathematically. So anything which is random, we go for probability based distribution. But here we are not going to model burst noise by Gaussian. Gaussian is a bimodal. Bimodal means it is going to have a bell shaped curve, and it is going to be symmetric. So if you exactly cut this graph into two halves, it will be exactly same, right? But this noise is not going to exhibit behavior of a Gaussian. It is going to be multimodal, which means it is going to depend on many more parameters. So I am not going to use a Gaussian distribution for modeling. So this uses a non-Gaussian amplitude distribution model, because the noise can switch between two or more discrete values at random times. The noise can repeat, giving the same noise power, or it can vary, or it can keep on varying between two parameters, three parameters, four parameters, but that is completely random. So we cannot predict that. So just like how we had an RMS noise power equation, we cannot very much exactly model this popcorn noise, because it was completely random in nature, and it depends more on the device parameters because of